Okay, welcome back to the second half of the session. First of all, thanks Niran for a great talk. We'll be now covering some war stories of people actually building large-scale systems and seeing some of the hints which Niran talked about being used, ignored, and so on and so forth. But before I go into that, couple of quick announcements. First of all the lectures and the presentations are available on the Turing100 website, on Persistent website, so you can just go there. The videos and the presentations are also available. And second, there's going to be a conference in Pune in December, format, and the last date for registration early registration is 7th December. Just want to remind you, this is conference on management of data, and we have a pretty exciting set of people coming in and presenting over there as well. So just do go and check it out, and the last date for that is 7th December. That's the early registration. Come to the second half now. So first, let me introduce Dr. Basant Rajan. He is currently the CEO of Pune-based Coriolis Technologies. He previously spent years at Veritas and Symantec, where he served as CTO of Symantec India, then Symantec Research Labs and development team of working on the Veritas Storage Foundation products. Dr. Rajan has a PhD in computer science from TIFR Research in Mumbai. Over to you, Basant.
So it's normally not good form to start with an apology, but I think I need to do so. The talk I was prepared for was more student-oriented. I don't see any students around, so please bear with me. So let's start off with, that picture is a little too small. What's on the right is a logging application. What it does is simply this, allows me to view logs in a way that helps me debug. So what does that normally entail? I need to be able to actually filter out log messages which are irrelevant to my investigation and concentrate on the ones I'm interested in. So what it means is I have a whole list and I keep filtering things out and whittle down the things to the relevant piece. The specification for that application is what is written down there on the left. This is actual stuff. This happened about a week ago, and I wrote this down and sent it to a kid. And this was the specification for the system. Well, take it one step further and you get all those set of equations on the left. And finally, it reduces to just those functions. Recursive in nature, but solves the problem. What was beautiful is, 4 days later, the kid comes back with the application on the right. Not systems research though. Very cleanly specifiable system, very useful, got the job done, but lacks the essential ingredient that Niran talked about earlier, saying it's not large, it's not complex, it's too easily specified. So that was just an example of what this is not about. The rest of this talk is about going on a design of a system, pseudo, share some experience along the way about a real effort in the same area, and part of that experience will touch upon the human angle to systems research, because not all of systems research is neatly representable on paper. A lot of it is feelings, because as Niran pointed out earlier, there is no best way of doing something. There's just an attempt at not making terrible mistakes. That's it. But I won't be following this order particularly well, so this, please be warned. So what's the system that we're going to be building? Let's define it. We're going to build a scalable file server. Pretty simple spec. Not so complicated as the previous spec was. No equations, no nothing. I assume all of you understand what a file server is supposed to be. Serves files. Scalable means extreme I/O. Fair enough? Lamport and Niran cautioned us that we need to start with an interface. Right? So here we go. You need to be able to create files, read them, write them, delete them. Reasonably complete set of requirements. Okay? Then comes this problem of measures of success. In the case of the previous problem, if it actually met those equations, we are successful, the program is done, and we are done and over with. In the case of a file server, what's success? I could write a file, read it back. Is that successful? Not particularly. If I could read and a million people could write, I'm sorry, the other way around. If I could write and a million people could read, maybe it's success. So normally in systems, you run benchmarks to decide whether your effort or what you came up with was worthwhile. So these benchmarks are very well-known loads that you shove on the system and see how the system stands up to that load. Okay? So it's like if you build a car, you take it on the Himalayan rally and see if it falls apart. That's what our notion of benchmarks would be. Now, again, as pointed out earlier, there is no gold standard. Whatever you come up with, sure as hell somebody is going to do a better job the coming year, 2 years from then, 5 years from then. So don't look for the gold standard, we'll just try to get a system together. There was also some mention about divide and conquer. So let's divide first. We will first do the reads. If I had a document that I had to give to all of you and want to get all of you to read it in the shortest possible time, what would you do? Photocopy the document, give each person one copy and be done with it, right? I could do the same thing with a file. What happens then? I have multiple file servers, like web servers, serving the file. Each person goes to some server or the other, reads it. Extremely scalable architecture. Simple, right? So, are we done then? Is there a problem then? This is a bit too early. Sharing, when giving each person one copy is a bit too expensive. I need to be able to say one person gets, many people manage to read from one copy. That's pretty much what a web server does. Right? Many people hit one web server, but there are multiple servers so that more and more people can do it. And you can do load balancing and what you end up with web servers, but that doesn't actually solve the rest of the problem. What's the problem that it doesn't solve? Who writes? There's a lot of complexity in handling that write. But let's park that for a moment and see, if you're doing systems design in the real world, what are the things we got to deal with? One of the things that keep coming up when you try to do a file system is the page cache and the virtual memory. All of you are CS guys? Okay, then bear with me please. I'll skip over this as quickly as I can. I try to equate this to picture frames, a video library, and seeking for a clip in an album or a movie. Okay? So you have files, but you can't read them until you have pictures in your video library. You can't see them till somebody loads them in a picture frame. That's the interface you have. You can look at the picture frame. You can request for a picture. But until somebody puts it there for you, you can't see the picture. That's pretty much how a real system works with data. The data is in a file. The file has to be loaded to memory, but you typically get access to one page of memory at a time. So your life is spent asking for the next picture, the next picture, the next picture, and somebody is servicing it and putting it there for you. If all this happens at the back end, then you can read. And all we talked about so far was just reading. Okay? So, again, there are interfaces that come into play. When we say we want to see a movie or read a file, what we are telling the machine at the bottom end is to say, this file, this offset, this length. That's all I'm interested in at a given point in time. Okay? Similarly, The first part of this problem is memory and the file system. Second part of this problem is file system and the disk. So the file system is akin to a library and the disk is akin to the books in the shelves in the library. Okay? Your classification of the library books is akin to your directories and file structure. The books on the shelves are files on the disk. The shelves, what you can do with them is you can place and remove a book, right? On the disk, the equivalent thing is you can read a sector, you can write a sector. That's all you can do. Absolutely nothing else. Copies of books in a library equal to mirroring. Forget that part for the time being. Reserving shelf space is allocating disk space. That's the analogy that exists between file systems and libraries. Why am I saying all this? We were only trying to do reads. When you're trying to build a file system that reads, you have to work with a system which knows about disks, it knows about memory, and it knows about page cache. You have to work with these primitives and come up with the functionality of reading a file. Already, the complexities involved are large enough. If that isn't enough, let's start looking at writers. The simplest way is somebody is writing, multiple people reading. How does our web server solution work in this case? Pretty well. Somebody writes, updates a web server, and everybody else reads and everything is fine. One problem though. There are copies and therefore there will be stale data. I could update only one of those files web servers in the beginning. So for some point in time, you either have to bring down the other web servers, in which case there's outage, or there is a guy who can get old data and new data at the same time, depending on which web server he hit. Right? This problem is at the crux of any scalable file system that you try creating over multiple machines. It's called cache coherency. You need to make sure that there's only one copy of a given data in the system. How would you solve this problem? You partition the space and say that the first 5 pages of the Constitution, let's say, will be reviewed and corrected by A. The second 5 pages will be done by B. No two people are writing the same page ever. Right? No corrections being done like that. How many of you have actually sent design documents around your team and spent hours trying to merge the conflicts? By the way, you guys do write design documents, right? Okay. So, when you do that, simple way to do that is say this module, you give it to so and so and say you update this one. This module, somebody else, update that. You end up partitioning the problem and making it a single writer problem. It's a simple way of breaking it down. It's better than the original single writer problem where we said that the entire document had to be updated by only one person. But it's still not quite there, because every problem we talked about in the single writer case is there in this case too, except that it is partitioned. So the scope of the problem is less, the issues are the same. Utopia would be where multiple writers could actually write. Everybody who reads gets the latest data, and never will you get stale data. Okay? So that's basically what our system needs to do. At this point, we have to introduce something called a reader-writer lock. Why? When the first guy tries reading, all's fine. As the movie goes, all's well. The next guy tries reading, all's well, same copy. Give him another copy, let him read. The moment one of them says, I want to modify, all's not well. you have to first recall all the copies of the data that everybody has so far. Then say, I own this data for the time I'm going to change this. And then say, I'm done with my changes. Now you can all share this copy again. So the duration when you own the data to the time you release the data for sharing is a protected time frame, where in closed doors you figure out what you want to do, make the changes, and then release it to the public. Those two parts are marked by reader-writer locks, by saying you take a writer lock, you release the writer lock. Okay? Now, why is this such a big deal? Let's assume that you have 3 machines, let's say 2 machines, each one reading a file on a shared disk. By the way, when we started building the system in Veritas, that is, I don't know, maybe 10 years ago, no, 8 years ago, somewhere in that time frame, it was one hell of a pain to connect one disk to 2 machines. Have you guys ever tried doing that? One disk, 2 machines. How do you go about doing it? So if you had SCSI disks, you had an ID on the SCSI bus, and you could have 2 controllers. So we could actually connect one disk to 2 controllers on the same cable or same bus. So remember, Niran was saying that when you're doing systems, typically the hardware doesn't exist. This existed, but not quite. This was not meant to be a use case for SCSI. Typically in a SCSI bus, you have one initiator and multiple targets. Here we were dealing with 2 initiators and 1 target. So there were some problems in getting that working, but let's forget that for the time being. So that was the first time we actually saw this happen. And we spent, okay, long story short, we spent, I think, 6 years before we got the product out. The team built 3 prototypes. Remember, there was something out there which says, be prepared to throw it away? We threw away 2. I mean, we built the entire thing. We went out there to do the release, and then the engineers got together and decided, this is just not scalable. Throw it away, come back to the drawing boards and start all over again. The first effort took 3 years, down the tube, straight up. One should say that we took one hint of Butler, throw it away. I mean, if we had followed the remaining hints, we probably wouldn't have had to follow that particular hint that early in life. But that was how it ended up. So that was our first attempt. How did it go about? How did it evolve? We put together a team, most of us out of college. So we didn't have any big shot file systems developers out here at the beginning. I mean, we were just out of college or out of grad school or something of the kind. We had enough experience with digging around in the kernel, but not much more than that. Morris Bach was our Bible, and that was it. From there, we start building these pieces bit by bit. And we came to the point where we could actually read the device from 2 machines. At that point, somebody from a group that shall not be named, actually did a write. So when I assume you're all CS guys, right? So I'm going to change gears and stop talking about libraries and books. We'll talk about comp science. You take a disk, you mount it, you get a file system. With me so far? Okay. Now, you take the same disk and mount RO on a different machine at the same time. Things would work. You will get clean read-only access to that file system because neither machine is modifying anything. Okay? We came to the point where we could get the hardware to work to do this much. At that point, a group went ahead and decided to do read-write. Well, they turned on one machine into read-write mode, went ahead, wrote to it, read it back and said, voila, we got the data. They sent out a mail, no joke, saying, we are not even the file systems group, and we've got read-write to work from multiple machines. And honestly, the first time we read that stuff, we were like, what? We've been breaking our heads on this problem for quite some time, and we don't have the guts to take it to read-write yet. And here's a team, not in the kernel space, done it and claiming success. Half an hour later, there was another mail saying this is just a bug. Once in a while, what we write is not what we get back. Okay? Once in a while. So the question was, once in how big a while? Okay? One in every third write is waste. Well, that's where technology was, so that's where the industry teams were when we started building a system. The general understanding of cache coherency, zilch. Okay? The general understanding of being able to do mutual exclusion across these kind of things for a shared resource, not there. Because can't blame those guys too, because they came from the same colleges that we came from. Right? We never done this before. They were trying, we were trying, we just spent a little more time reading Morris Bach. That was it. So then what happens is, we try putting the right capability in. This is fun. The previous presentation had this topic about splitting resources if you want to. What was it? What was it? Hint there? I don't remember. Yeah, you can share more easily if you split the resources. Okay? So what did we do? Smart guys, share resources. We split the disk down the middle and said, okay, free blocks, half this fellow takes, half this fellow takes. You do whatever you want inside this. You can do allocation from your free block, you can do allocation from your free block. For all practical purposes, you're working on two different file systems. Right? So long as you work in directories which do not overlap, this works. When you start working with directories that do overlap, that pesky reader-writer lock needs to be shared across two machines. Bit of a problem. Okay? So that was fun getting there. Let me go back to this presentation and come back to something called caching. What's caching? You take a disk, you read from that, and you're done. You would think so. But as I said before, the disk is actually twice removed from the guy who's reading. The disk interacts with the file system. The disk is there's an IO layer which interacts with the file system. The file system interacts with the page cache. The virtual memory system. The virtual memory system is segmented by pages, and all this got to work together for you to be able to read this file, or read one page in that file. Now, if the second guy in the machine tries to read the same file, what would you do? Going back to our paper copy, we would go to the press, make another copy, give it to him? No. We would just give the page that is there to his neighbor and say, read that. Right? Share the page in memory. Don't go ahead and do another read from disk. Right? That also was covered by Butler. He said cache. Right? Cache the function fx and fx. The function, the arguments, and the result. What's the function here? Read. What's the argument? The offset, where in the file you want to read. What's the result? The actual content in that space. Right? So if you have cached it, you could serve that data or that read from memory. Much, much faster, more than 100 times faster than reading it from disk again. Okay? So we said we should have caching. So what is caching involved when two machines are involved? There's one machine which has a disk, when the disk is common, let's say. There's a machine which has read portions of the disk into its memory. And so somebody reading it from there. There's another machine who's trying to read the same page, and another client trying to read the same page on a different machine. He has the option of reading it from disk, populating his memory, and giving it to the client. But if we are to follow Lamport, we should make use of caching. We have seen this read before. We should just retrieve the result from the cache, which in this case is memory. Small gauge. Lamport didn't talk about that part. I'm sorry, Lamport name. Lampson didn't talk about that part. By the way, Lamport is also a big guy. He will show up in these lectures down the line, I guess. Right? He didn't talk about what happens when the cache is distributed. At least not in the hints. What we had to solve was this material was cached, but on the wrong machine. Okay? What's a smart thing to do? Instead of going to the disk, send a request to the other machine and say, give me that page. Fair? That's exactly what we did. Now, after a while of doing this, if you say 4 machines there, you have 4 copies of the same file or same page distributed. Now, if this is equivalent to saying each of you got your photocopied pages. Now somebody said, I need to correct this sentence. What do? Go and correct the sentence in all the 4 copies on everybody's photocopy here? Not doable, right? So what do? You send out a message saying, all of you who have this page, throw it away right now. Purge the cache. I will update my copy and now say, if any of you are interested, read it back from me. Right? The reader-writer lock that we talked about earlier ended up taking on a global meaning. It was not a local thing anymore. That was one of the first things we had to solve to create file systems across clusters in Veritas. Okay, I use the word Veritas and semantic interchangeably because most people change jobs. In my case, the company changed on me. I joined Veritas and got bought over by Semantic, and inertia kept me where I was. And company changed. So that's that. So we came across, we discovered or rediscovered or reinventing is probably an okay word to use because it actually was reinventing. It was not invention at that point, but we reinvented syncing off the network. We had to move pages across. Now this brings us to the human factor. We were the file systems group, the networking group was different. If we have to communicate with another machine, we have to use networking routines developed by somebody else. First off, what do? Try not to. Right? Everything we do, we build. But in real life, it doesn't work. Somebody with better sense upstream knocks it down your head that, no, you will use the networking team's help to do this. So, well, we go to the networking team and say, give us something that will give us one page from the other side. He says, I don't want to know about pages. You give me a packet, I'll give it to you. Fair enough. So, as talked about earlier, there was a simple interface that the networking guy said, I will give you a method to transport blobs of data, whatever they are, with low latency to the other side. Okay? All very well, except they forgot to tell us some of the assumptions. Remember, there was an assumption that said, if the load goes too high, drop packets. Well, they did follow that as that hint. They just didn't tell us that. Okay? So we asked for a page, data to be transferred. The load went up. They dropped the packet. We got nothing. What did we do? Well, nothing is there in that, so we write whatever we want. Started messing up again. Well, there was more trouble when you say human side of it. Have you worked with multiple teams on any project, large project? Dependent teams, right? Have you ever managed to say that this bug is yours? Rather difficult. Very important part of distributed systems development. A nice way of objectively saying, not my problem. Okay? Politely say, this is on your table, deal with it. It took us well nigh a year and a half to figure out how to do this. And in the process, guess what? We built a system to prove that this was their problem. No joke. We had more code to show that a packet loss was happening in the transport layer than they had to actually send the packet across. So the test system was way more complicated than the system it was testing. To the point at some place somebody said, why don't we use the test system as a transport mechanism, because every packet that fellow sends, we send on a different channel to see whether it was all right. So the guys who did the test part actually built the same capability, different code base. And it is, trust me, extremely interesting to be in those meetings where you're trying to lay blame on somebody else's door. A lot more difficult than anything Lamson talked about. Systems research pales into insignificance at that point. Now comes granularity and overheads. Now we talked all the time in terms of pages, right? It would be really boring to say then, oh, did you read page 35 of that book? You read in chunks. The chunks have to make sense, right? That's where granularity comes into picture. You do not deal with system-specified 4K pages or 8K pages. You deal with user-specified blobs of data. So you want to deal with the granularity that makes application sense. The system wants to deal with the granularity that makes sense to itself. So for instance, after all these years, the disk still works on 512 byte sectors. When was the last time you had a file which was 512 bytes? You start up a Microsoft, man, any die-hard Microsoft fans out here? Okay, you start up a Microsoft Word document, do nothing on it and save it. Any idea how big it becomes? That's more than 512 bytes. But our disks still work on 512 byte sectors. Why? Well, I don't know why, but what we use it for is simply this. That 512 byte sector write is what we call an atomic write size. Okay? What does it mean? If I do a write to a disk of say 1 MB, I am not guaranteed, there is no guarantee that the disk gives me that all that 1 MB has been written. Okay? But if I tell him to write 512 bytes, he gives me a guarantee that this 512 bytes either all there or not there. If I told him to write 512 in 5 MB, he might have written the first 1 MB and then died. So assume you were writing a story and you were overwriting the story or editing something, half the story is different, the rest of it is old. That guarantee is not given by the disk unless the size is limited to 512 bytes. So the granularity in different parts of the system are very, very, very different. Today we deal in terms of, I copied this file, I didn't copy this file. At the bottom, they write 512 bytes at a time. Not really 512 bytes at a time, but that's all it can guarantee as written or not written. Okay? What happens when you change the granularity is a lot of overheads change. Remember, Neeran talked about an interface becoming chatty? What it basically means is, if I wrote a 50 MB file in 512 byte sectors one at a time, what happens? I request, he responds. I request, he responds. I spend more time requesting and responding than actually writing. Right? All that goes into design decisions on what granularity you'll work with. Content, and that follows down into contentions and bottlenecks. Real life scenarios, we have contentions on various things. Any of you here die-hard Unix guys? Okay, cool. All of you use the /temp file system as though it was your inherited property from your inheritance, right? Any temp file you want, you open up there and you write to it. There are systems where it's a pretty large system, so basically say 512 CPUs. It also has only one /temp file system. If there are 512 CPUs and let's say 10 processors per CPU, just think of the number of processors running on that. All of them are trying to write or create files in the /temp file system. What happens? You end up with extreme contention. Why? When you try to create a file in a directory, you got to make sure the file name is unique. It doesn't clash with something else. Right? If 512 into 10, 5,000 guys are trying to do this on a regular basis, you'll be looking at a pretty large file system and file directly there, and it's going to take a lot of time to figure out whether it's unique or not. Because we made some terrible mistakes in our original design. The directory is not multi-level hashed or anything, it is just basically a straight list. So if I want to find if a file name is unique, I have to read the entire list and see. No, I can create this one. Now there are a million files out there. When I want to make the 1,000,001 file, for me it's the first file. But for /temp it is the 1,000,000+1 file. It has to read all million file names, do a string compare and say that, this one is unique, go ahead. Right? What do? Break down the granularity and fake a /temp file system. You create multiple /temp file systems and make it look like one. You say all files with A start from this file system, temp A. All files with B start with temp B. And you basically then can reduce the problem and make it more tractable. Right? Again following Lamson's divide. Makes things better. Now let's come back to more real life problems. We build a system. What happens because there is no gold standard? How many times have your designs been trashed by somebody else in your group? Never? Never? Something is going wrong, man. So think of a group which has about 40 people. All of them raring to design the next biggest thing in the industry, clustered file system. Everybody poring over every design detail of everybody else. What happens? You have design by committee. What it means is, oftentimes we make terrible mistakes. When do we figure out? We finish prototyping, we build the system, the perf lab comes on board, starts pounding on the system and say, nah, we can't expose this to clients. What do? Go back. And what do? Design by committee again. So one of the things that we learned out of this business was, get rid of the committee. So you partition the space and you basically make specialists in each space. And you say that he is the ultimate authority that you got to go get sign off from for this part of the file system. Anything related to this, he does it and we're done. Partition the problem, granularity goes away, and by the way, this becomes a lot more messy when the teams are not in the same place. So many of these people who are commenting or ridiculing or basically improving your design, you haven't seen before. They're just email addresses. Okay? Makes it very difficult to accept even constructive criticism if you don't know who it's coming from. And sometimes it makes it very difficult if you know who it's coming from. Okay? So when you have large systems like this being built with teams which are separated, one of the things that we learned from comp science practice was to use systems engineering principles in team management. Divide, make specialties, basically create clear interfaces saying keep your nose out of this pie. Because if everybody puts their fingers in everybody else's pies, we don't make progress. Because there is no gold standard. I come up with a design, sure as hell, 40 smart people can come up with, 5 of them at least can come up with one better design. Then we start defending that one. We keep doing this, we never build anything. Right? So, one of the things that we learned building these systems was break it up, not just the technical side, the human side as well. Makes it a lot more tractable, much less intimidating. Just think about sending out a design doc to 100 people for review. He wouldn't write the doc for fear of what's going to come back in the review. So we build this up hierarchically. You create a doc, you circulate it locally, then the local comments are taken care of, then you send it one level higher. What happens that way is you get strength in numbers. You get beaten in college, in school, nobody's really that bothered if everybody got beaten along with you, right? So if it's your individual design that gets messed up by reviews, feels really bad. If your design was signed off by your peers and then it got messed up by somebody else, you take 1/10 of blame. Feels a lot nicer. Okay? We learned that too. Once we built all this stuff, we got read writes to work. We completely hadn't thought about, shouldn't say we hadn't thought about it, we hadn't prioritized this fault tolerance part. What happens if one of those machines dies? But some things we got right following those principles from Lamson. Don't optimize your algorithms for the case when one machine dies, because it happens only once in a while. So when it does die, we go into a mourning state, go around checking to see who has which lock, tell everybody who owns these locks, please give them up right now, we'll start afresh. What happens then is, what is an RPO? It's a recovery point objective, and that is how far back in time do you end up having to start from again? Does that make sense? Okay. And what's an RTO? Recovery time objective. And how quickly can you get up on your feet again? Okay? So you're talking to a team which built a system that's clustered, and its individual system once took 2.5 hours to boot. Single system failed, coming back up took 2.5 hours with no errors. What would be your acceptable time frame for 20 machines connected together, each of which is of this kind, to come up from a failure? We wouldn't meet that criteria, but Anand wants few seconds. But yes, the idea was we needed to get there under a minute. I mean, if we took 2.5 hours to recover from one such crash, and I don't remember who it was that described a distributed system as one where some machine somewhere that I hadn't heard of failing would cause my work to get interrupted. I think that was Lamport. I'm not sure. But the idea was the individual machine takes 2.5 hours to come up. The cluster should recover in under a minute. So what do? The moment you detect one machine is dead, this is exactly what you do in politics. You have a splinter group, you eject him from the group and basically consolidate the remaining MPs in some hotel and say you can't talk to anybody. Right? That's exactly what you do in computer science. One machine is considered failed, you eject him from the cluster, tell everybody else he is a pariah, no communication with him allowed, we will elect another leader and get on with life. Okay? That's something that we have to build into our system. Doing that in a distributed manner is actually an exercise in itself. We'll do it some other day. Logging is something else that was touched upon in the previous lecture. That is really the only truth. What you see is not the truth. What your children see through history books is the only truth. It doesn't matter if you don't think so. That is the only truth. So if it is not logged, can't be replayed, it ain't true. So one of the things we had to do was do everything that we do in this cluster in a logged manner. With one caveat, the log is not in one place now. Each machine is doing logs of its own. It's like many historians. They have different versions of history, but because we were comm science people, we could make sure that all those historians wrote the same kind of history. So we could merge them together. So sometimes it's good not to have politics. Leader election was something interesting. I mean, we haven't solved it in real life. We haven't solved it in comm science either. What we do is a best fit approximation. In government, we say the guy who got 25% votes of the population becomes the ruler. In comm science, we say whoever got there first got it. Okay? It's nothing more than that. Well, state recovery is something else that we had to do. What's state recovery? One machine died halfway through. You can't abandon all the clients that he was servicing, right? We have to pass them on to some other machine. Get that done. Replication is something that we didn't do. We ought to have. So I won't talk about that at all. Okay. We started off with paper copies of a document that we could send out to read, bringing them back, making changes, sending them out to read. Along the way, we ended up seeing that it's not that simple. Interesting thing is, we actually built that system. It took us 6 years, 3 attempts, and proud to say, was part of a team that built the only, the industry's surviving cluster file system. Enjoyed the time, mistakes, successes, everything. Was lovely, and I really hope you guys get the chance to be part of similar efforts wherever you are. I said more or less because work's still continuing, because there is no gold standard, and every year somebody comes up with how we could improve on the previous design. Okay? Thank you. Questions? I doubt there will be questions on this one, but if there are any comments, please. No? Not really. The problems cache coherency still exists. All that SSDs change for you is the latency to disk is lower. There are a whole lot of problems that are very well hidden by the SSD manufacturers. Again, following on Lamson's advice, that is, when you write to an SSD, you need to make sure that the number of cycles each cell uses is minimized, because SSDs today have a lifetime, and you got to keep writing in different areas to load distribute that stuff. We don't see that stuff at the systems level. That's happening at the controller level for that SSD guy, right? It's not becoming any simpler. It's just as complex, probably more so, and it doesn't change the fundamental problems that existed in the CFS space. Some things are there, like you don't need to bother about fragmentation maybe, like sequential reads and stuff like that. We've tried a lot to make sure all the file is in the same contiguous blocks on a disk. Didn't quite make sense since SSD time, I would think. Anything else?
Yeah. So
yes.
Yeah, one question from Nagpur.
Hello. Nagpur, please go ahead.
Not a question, rather it is a doubt. So you were speaking about multiple controllers using one disk.
Yeah.
For computing, and if I'm copying a file and it is stored in my cache or virtual memory, the other controller might it would be faster for him to, less expensive for him to copy it from my virtual disk other than going to the disk itself. You said that if I don't like a line and if I want to change it,
yeah.
So everybody else, I won't go to each file and change the file, change that line in the file. I would rather say everybody else who has this copy would throw away the file, and whoever needs it now can copy it from me, from the client's virtual memory. But if in the same case, the next time, the file is not updated permanently from the disk, is it?
I'm not too sure I got your question right. Let me see if this is what you were asking. Yes, if a file's contents was cached in multiple machines and one of them needed to update it, what the protocol followed would be something like this. The guy who's going to update it will intimate everybody around saying, I'm going to update this page, drop this page from your cache. In our words, purge it from your cache. Okay? Now I will update my page of it. I will schedule it for background write into the disk. Again, following what Lamson said, what is not necessary to be done immediately, background it. And I'll tell everybody else, if you need to read this data in the interim, contact me. I will give you a copy of the contents over the network. Does that answer your question?
Yes, sir. The background thing, it did. If in a scenario that I want to access that file after 10 days.
Oh yes, it had to be on disk by that time. So the background part had to be not that much of a background. You can push it out from. Yeah, is that okay?
Yes, sir.
Okay, thank you. And anything else?
Yeah, the question I had was, now with all the stuff that's happening with things like Amazon, go on the cloud for many of these kinds of things.
What was the relevance of doing all this?
No, I'm not asking the relevance. It's a slightly different question. See, as you see over the years, the level of abstraction at which people have been working has been going up. To a point where most of us are never going to write an operating system.
Thankfully.
Any real value. You would write one for class projects, but you know that it's not likely to happen. Like this, perhaps this is also kind of.
That's it.
People in the world may have written it, and that's pretty much it. And if you move on, some other things will have to be done. So, what's your comment on that? The fact that are we making a big deal out of some of these things, and should we stop worrying about all this problem because very few people need to worry about it and just focus on the application and the stuff that runs on the cell phone?
I would agree and disagree on that. Okay, just to repeat the question.
It's going to be a provocative question.
Yeah, just to repeat Anand's question, the question is, given that the world is moving towards higher and higher levels of abstraction, and basically today's systems is actually the cloud. It's not the nitty-gritty disk that you're dealing with and things like that. In that context, does systems research have any meaning? I mean, are we giving it far too much importance today than necessary, because the action seems to be in the build the application space? That's the question. Yeah. So, yes and no. The vast majority of people who call themselves computer scientists will not see a real system in their lifetimes. That will be more true going forward, and I think that statement will remain true as a time invariant, that less and less people will see the bottom. So in that sense, I agree with what Anand says, that we are making a big deal out of systems research because that's not where the action is, right? But as and when these people move forward and go up the abstraction layer to build these large and wonderful systems, there's somebody, a small set albeit, who have to work towards implementing those abstractions on ever more complex systems beneath. And what's interesting is the systems research probably has actually it takes on a different meaning now, in the sense that it has to actually take care of a wide variety of hardware. Earlier, you say you had a disk, it's over. Now we know if you wanted to put an SSD disk in there, you have to have a different set of controllers for that. Who's going to be building all those? With a poor guy called a systems engineer, right? There won't be very many people doing it, and certainly they will be hidden away in some place that you don't want to go to. It's not going to be Disneyland. There are going to be very few people who actually go there. But it's like saying, let's say, you can't not spend effort at the grassroots level in the hope that you can live with whatever exists today and keep building on the top of it. The base is changing, and there has to be somebody who bridges the gap between the castles in the air that the application abstractions are building to the actual mortar and brick and mortar that is required to hold up this edifice. So we talk about cloud computing today. Yes, beautiful interfaces, you don't need to know where they stand and stuff like that. When where your data is, you get blobs there and you can move things around. Talk to Niran more about it though. But what does Amazon have to do at the back end? Still has to deal with PCs, commodity hardware, actual hardware, disks lying all around the countryside, and eventually still store the data and read it from it. So the number of people doing cloud computing is increasing by leaps and bounds. The number of people doing systems research is a shrinking community, at least in percentage of the total. So in that sense, I agree with Anand that this is the past. This is the past, and the future is the abstraction above, and getting better and more powerful abstractions on top. But I disagree to the extent that it does not, obviate the need to have systems engineers. That I think will remain.
We are giving too much importance to the word systems. The way one should interpret it as whether you are working in the system level, the one we hear about, for example, earlier, system programming is nothing but an assembly language programming, right? Then came, if you write in C, you're a system programmer, right? But then you have seen a lot of applications developed using C. So I think undue importance is given to so-called word systems. The way one should interpret it as large, complex entities. Okay?
Fair.
Even if you are working in cloud, you are going to build a large, complex entity.
The nice thing is we call that systems now.
Yes.
I mean, building of the cloud is systems engineering.
Hints he has talked about
Yeah,
are, equally important to any large complex.
I agree.
Yeah.
I agree.
That's the way this has to be treated.
Anything large will benefit from those hints, not necessarily
That's
below the kernel.
That's the way one should view it.
Yeah.
It's not like kernel.
Then-
It's a complex.
I agree.
You need to tackle.
I agree
You
with
need
that.
to divide and conquer. You need to kind of come out with interfaces. These are fundamental truths. These are
I agree with them wholeheartedly. No issues there. By the way, just another one of these crazy things. We had a kid straight out of, I think it was IITB, joined us, great kid. Was working in the kernel with us. His parents had a real problem with him. Says, बेटा इतना सब पढ़ के भी आप ये low level काम ही क्यों करते हो? Because he described himself as a low level kernel engineer. And his parents honestly had a problem with, after doing so well in academics, why can't he actually move up the ladder a bit? So, yeah, this is low level, high level and stuff like that are just tags. And what matters is, do we get the jobs right? I think that was on his first slide, right? The hint, get it right, make it work or something like that. Yeah, that's true.
So I actually have a slightly different answer to Anand's question.
Yeah.
It's just that, yeah, I mean, more and more of the world is doing simpler things. The thing is that after a few years, the lawyers and the doctors will be building applications, and if computer scientists need to stay relevant, this is the stuff we have to work on.
So Naveen says that this is our job guarantee scheme.
Even the lawyers and job to build a system which would understand the lawyers and doctors' language, right? And so you need to.
By the way, we tried natural language processing and whatnot.
Then the natural language processing will also mature because there are various techniques coming
Yeah.
up. So it's going to evolve. Yeah.
Also, basically, maybe we should be churning out less computer scientists and more of the other professions, but that's a different argument.
So I guess we are done. Okay. Thank you. Thank you, guys.